when we put the data in the cloud, we put it for different reasons, but definitely one thing that we want to do is to use it for something. And usually we want the cloud not just to store the data, also do something with it. And but the data is exposed to the cloud, so you would like to encrypt it. But then if you encrypt it, how do you use it? So the typical solution is to keep the data encrypted while not being used, but then you decrypt it for computing on that data. So what you want to do is to encrypt the data with your own keys, put it on encrypted form in the cloud, and later being able to do something useful with the data without having to decrypt. Then we have, as Vinod told us, ways of doing this in very general ways, but since these general ways are not practical enough for real-world applications, then we're looking for specific functionalities that we would like to apply to the data, and one very basic functionality is search. So the question is, can we keep the data encrypted while still being able to search in it, again, without having to decrypt? So this brings us to this notion of searchable symmetric encryption. Again, you have an owner of the data, which takes the data, encrypts it under its own keys, process that data and the encryption, and put the result on the external server in the cloud, while keeping only a small state. You can think about just keeping a cryptographic key. And later, this owner of the data can take any query, encrypt the query, send it in encrypted form. The server does not decrypt the query, but it can take the encrypted query with the encrypted data, find the results, and send them back to the user. So, for example, if you are storing your email, then you may want to do things like give me all the emails with Alice as recipient that were not sent by Bob and containing at least 2 of these words. That's the type of search that you would like to do on the data. And the goal is that the server returns the matching documents without learning the plaintext query or the plaintext data. In order to be efficient or practical, we are going to give up on some of our beloved fully computational security and allow for some forms of leakage. For example, maybe the main thing that we are going to do is that we are going to return encrypted documents, but if the same document is asked for twice, I mean, 2 queries have a document in common, the server that stores the encrypted data will know that this document was asked twice. It will not have the plaintext of the document, but it will be able to learn stuff from that. We also do things like we do, if a query repeats, then the server learns that the query repeats. So the plaintext data of queries is never exposed, but there is statistical inference from which you can learn information about the data.
The server can learn how many matches there are, whether there is a match, how many matches there are, right?
Right. So the server returns, if you think about returning documents, it knows everything about these documents except the plaintext. So it returns the ciphertext. So if there are 2 queries with intersection, you know about that. And how many results. There are some things that you can mask, pre-process things with some masking, but that is basically what you get. So by the way, one of the things, so you protect against break-ins, against insider attacks. I mean, the cloud itself, the data is protected against, and even surveillance attacks that are famous in the last years. So basically, with this kind of technology, the cloud cannot disclose the data, even at gunpoint. So, you know, if a European company puts the data on an American cloud and the NSA comes after the data, the cloud itself cannot give the data because it doesn't have the keys. Okay?
If I just see the encrypted data, is it semantically secure as in without the tokens?
Yes, I mean, I'll say that. The question was whether the data itself is semantically encrypted under semantic secure encryption. So the bulk data is encrypted. But so I'll say that. So this work was motivated and funded by an IARPA project, which is like DARPA, but for the intelligence community. So before that, what we had basically is, of course, on one hand, these very, very secure but very heavy tools like FHE or PEER, very expensive in practice, but great security. By the way, when I say great security, is assuming that you apply the FHE or the ORAM to the whole bulk data, because otherwise you go back. I mean, if you only protect the processing of the queries, but you go to the return, you know, the documents are still encrypted under regular AES, and you return the ciphertext, then you have that same leakage that I was talking about. So it's really expensive to do that, at least for big data, and that's the subject here, right? Big data. So. And then you have another option of doing it, that was being done before 2013, is to use deterministic and order-preserving encryption. And the cryptDB system is maybe the most famous of the systems that use this approach, which actually is quite practical system, but also has very significant leakage. And we will have a talk by Seni Kamara in the afternoon about this topic. But just to give you an idea, when you do deterministic encryption, so you have a column of name and last name. So basically, deterministic encryption means that if an entry in the database repeats, then also the ciphertext repeats. So for example, if you see the names and you know that John is the most common name, then you can at least guess that the most common ciphertext corresponds to the name John. Then you have also order preserving to do queries, you know, like range queries. Then if you use order preserving encryption, in this case on the H column, what order preserving means is that you encrypt it to some randomized values, but these randomized values keep the ordering, the original ordering of the data. So for example, if on the H column you have all the ages, you know, you have ages between 1 and 100, and you happen to have a large enough database with all possible values, then basically you are not hiding anything because you have, you know, a full ordering, and you know the smallest one is 1 and the largest one is 100 and everything in between. So this gives a level of protection to the data, but also you know, gives a significant leakage. So since we see that we have strong security but not so practical, and practical but not so secure, so basically we are in a game of security, functionality, and performance trade-offs. This is what these works are about. And where you are in the trade-off, if you're happy with that or not happy with that, depends on your personal beliefs and the application that you are trying to address. So if we go now to this world where things are more practical and trying to reduce the amount of leakage, so we had dedicated solutions for single keyword search. I mean, if you just wanted to search by one keyword, give me all the documents that have the word Vinod, then Vinod was all the time referring to me, so I'll refer to you all the time. I'll show you how it feels. So if you're looking for vnode, then these solutions would give you, and these solutions are privacy, I mean, we have solutions there that are privacy optimal in the sense that the only thing that they leak is this document ciphertext that you return and whether a query repeats. I mean, if you're querying twice the same keyword, you'll know that. For conjunctions, there was surprisingly very little work at the time that, of course, you can solve it by doing n single keyword searches and finding the intersection. The only work that was more advanced than that is the work, it's too long. It passed too long time from the last time I gave this talk, so now I don't remember the. So what's that? Anyone knows? Huh? Right, Staden and Waters, right? So anyway, so this does conjunctions, but it's linear in the database, so you have to go and check basically every document or an entry for every document in the database, and clearly we don't want to do that. For large databases, you don't want to be linear in the database. So there are many practicalities, limitations to this work. Of course, single keyword search is not something that is too useful by itself. There was very limited support for data that changes. Designs were not scalable, particularly if you want adaptive security. No good I/O support for large databases, and not too much information about experimentation and prototyping. So the work I'm describing here, or I'm talking about more of the what and not about the how, extends this state-of-the-art in four different ways. First of all, it provides much more query functionality than single keyword. So we do conjunctions. Actually, we do general Boolean expressions. So you can do any Boolean program, actually, on a set of keywords. You can do range queries, and we can also do things like substrings, wildcards, and phrase queries, all of that on encrypted data. And we can do that on databases, structured databases, relational databases, or unstructured data like free text. Again, since we are in a big data workshop, then it's important that we talk about scalability. Basically, we can perform these functions on database of several terabytes with millions of documents or records, which means also billions of document keyword pairs, which is the real measure here, which is how big the index of these search functions is. And we can support dynamic data, allowing to add new records, modify them, delete them. And this was an implementation that was carefully checked and tested by a third party. In this case, the IARPA people, in particular Lincoln Labs, was doing this painful work. We and they worked very hard. Another property of this project, another requirement, was to have provability. Provability means that you have imperfect security because you allow for leakage, but you have to define your leakage functions to say exactly what you are leaking and prove that that is what you're leaking and no more than that. Basically establishing an upper bound on the leakage that you provide under well-defined adversarial models. So these are three dimensions in which there was an improvement. The fourth one is extending the application settings and the trust models in which this search on encrypted data works. So while in the basic searchable symmetric encryption, one usually assumes a single client. I mean, you take your data, you put it in the cloud, and then you are the only one to search on it. Here we are looking at the multi-clients, meaning that there is still a single data owner that does all this process of putting the data outside in the cloud, but it allows different clients to search on the data when you authorize clients by whatever policy that you have. So the client will come to the data owner or a proxy, someone representing the data owner, and will come with a query. The data owner will see if that entity is allowed to do that query, and if so, it will give tokens for searching the data at the server. So for example, a hospital will have a policy that a physician can access certain data, administrator can access another type of data, an insurance company yet another, so you can support that. And finally, you can also support something which is called blind authorization, which means that the authorizer of the query does not learn the query. Okay, so the hospital will authorize the query, but without learning the values on which you're searching. In our particular solution, the authorizer will learn which fields you're searching on, for example, whether it's a name, last name, and zip code, but it will not learn the values that you're actually searching. And this blind authorization assumes non-collusion between cloud and data owner. So the external server and data owner, if they collude, they can learn the query. Otherwise, it's protected. Now, this is a multi-reader, but it's still a single writer system. We are not using public key encryption here. There is only single data owner that can write to this data. Okay, so basically I was saying that we support this big data. So the actual results of this project and experiments is we support arbitrary Boolean queries on all these models, single client, multi-client, oblivious authorization. And the biggest database that we run this on is a database that has synthetic census data, 10 terabytes, 100 million records, and something like 100 billion index record keyword pairs. To give you an idea, this is like taking a database with one entry for each family in the United States and having 1,000 keywords attached to each one, where 1,000 keywords can be all kind of census data plus notes, some English notes. So that's a big one. And we run it on the smaller databases from an Enron email repository to a clue web, which is some subset of web pages that include the English Wikipedia. So if you are interested to search Wikipedia while it is encrypted, we can do that for you.
So there I don't care that Wikipedia is encrypted. I care that my query is encrypted, right? So is there a way you can do better is there a way you can do better if the data doesn't have to be encrypted? Only the query does.
Yeah, the question is whether we we can run queries on encrypted Wikipedia with encrypted queries, and you can think that makes sense if you want to hide your queries from Wikipedia or from the server. But then the question, if the only thing is you want to hide is the queries, then can we do better? I mean, without actually doing encrypting the data. I don't know the answer. I have to think about that. I only think in the shower. Huh?
This is already great, but you can be Greek, right?
The what?
You can be Greek.
Just kidding. You can keep asking questions, Vinod. So, yeah. But the truth is that it's very hard to hide information about the query if you see the results. So it's not clear. Okay, so we extended this stuff to support range queries, substring wildcards, and phrase queries. This gives you something like a 5x performance degradation, which means that you can support smaller databases, still big ones, but not as big as that one. And again, we can support dynamic data, changes to the data. Now, the scalability, basically the pre-processing scales linearly with the database size. Of course, that's what you expect, but it's not worse than that. In the examples that I gave, this goes from pre-processing of minutes to pre-processing of days for several days for the big database. All of this is parallelizable, so in that sense it can be improved. And it goes up to the implementation by really choosing carefully the data structures and the crypto and also I/O optimization, input-output optimization. And one nice thing is that if you have an improved algorithm for single keyword search, we can actually use that to improve the whole performance of this system. The search part is proportional to the number of documents that match the least frequent term in an expression. Basically, if you can write an expression like W1 and any Boolean function of W2 to Wn, these are keywords, then the search will be proportional to the number of documents that match W1. The communication itself is a single round in which the client sends tokens, gets back the indexes of documents that match the query, and now the client can go and retrieve the documents. And the query response time is basically competitive with plaintext queries. There is quite a lot of variability depending on the query and depending on the data, but at a high level and without getting into exact times, that is what happens. It's competitive. Here I just chose one example of in 100 million record with 22 billion index entries, a query like first name equals Charlie, sex female, and not any of these states, took 4 seconds. And so, it's at least in absolute terms is a reasonable time. So a lot of crypto design and engineering synergy and working between the cryptographers and the engineers you need for these kind of things. I'm not going to get into the actual data structures that we use, but one thing I want to say is that we work very hard to not to do anything which is that you assume that the data is RAM resident or your metadata is only on RAM, so you can scale beyond RAM and use disk accesses. And for that, there is many optimizations that are needed for that. The cryptographic operations that we use are mainly from elliptic curve cryptography. The nice thing is that I/O operations take so long, relatively speaking, that you can do 4 minutes. You can do many exponentiations per I/O access. Something like, we got to 1,000 exponentiations per random I/O access. So in that sense, when we have big data, the crypto is actually quite for free. If you have small data, that's not the case. To the question of how we encrypt the data itself is encrypted with regular symmetric AES, semantically secure all of the other games are played on the metadata. Now, security, what I call the challenge of being imperfect. You know, in crypto, when we can't prove that bad things only happen with negligible probability, we are very happy. Unfortunately, when you face these kind of problems, you have to give up on some security. And now trying to measure how much you gave up is not a trivial thing. But luckily, we have all the crypto models that are applicable also when you are not in necessarily the perfect security. So you have all these simulation-based ways of defining security and being able to actually give good descriptions of the leakage that you provide. So you provide leakage on access to the data and repetition of queries, and then each one of these systems has some more peculiar ad hoc kind of leakage that needs to be judged on a per case basis, per case solution based and application based. So let me see. Okay, security proof. Okay, syntactic leakage versus semantic leakage. These proofs tell you, mathematically speaking, they are good. They tell you leak this, and this, and that's it. I have a long minute to go. But the real challenge, there is a challenge in building the systems and proving them, but then the next challenge is understanding what this leakage means. Okay, and this is something that we will hear about the things in the afternoon. And actually, I'm not familiar with all the work that will be presented, but I'm sure that there is still a lot of work to be done in this area. And I would encourage everyone to do that. In a practical sense, since I sometimes wear an industry hat, then the question is, does the world need more than CryptDB? Isn't CryptDB sufficient in practice? And the answer is, for us, cryptographers would say no. But the truth is, the question is, what is your application? Who is your adversary? And these are not easy questions to give. Okay, the basic ideas are easy, so we'll skip them. I wanted to mention that this project, there was another team, Columbia and Bell Labs, that developed a solution for the same problem. 10 minutes. 10 minutes. Okay. Okay, let me go. I'll explain to you the ideas here because they're nicer than ours. So this is a conceptually simpler solution, which and more elegant, but it uses RAM resident data, so it's less scalable. Research question. Let me just say this because I think it's important. So we have this practical stuff. We have the impractical stuff. We would like to understand better which portions of the impractical stuff can be put into the practical one without destroying practicality, but improving security. Not much was done in that thing. Fundamental limits. We leak some stuff that you cannot avoid leaking, except if you do some crazy masking preprocessing and stuff like that. We have very few results about which one of these limits is inherent and which ones can actually be avoided. As I said, semantic leakage, understanding what leakage means for a specific application, and what we'd like. Of course, you can take an application and say, for this application, this is good or not good, but what we would like to have is more general theory that will let us reason about the things. There is differential privacy that we always think as a model that we would like to have, a general theory, but we don't have anything like this for these cases. So I think that, and of course, in a more practical way, sense, we support many queries, but we don't support a full SQL query set. For example, we don't do joins, which is very important. So there is a lot of work to be done in this area. Okay, I think that I went over my time. I can go back to the Columbia solution. Okay. Anyway, thank you very much.